Welcome everyone. For today's prep, we're going to look at the fundamental theorem for line integrals. So this theorem, let's read through it. So this theorem says if we have a curve C, and this is a smooth curve, and we have the parameterization R of t, where t is between a and b, and we have some differentiable function little f, and we could be talking 2 or 3 variables here. Either one's okay. And we have the gradient vector field del f here, and it's a continuous vector field. Well, then calculating the line integral of this vector field over curve C comes down to just evaluating the potential function at the endpoint, calculating the potential function at the start point of our curve, and then just subtracting. So when we do this, we're calculating the line integral of a gradient vector field. And let's just remember what that looks like. That's where we have some function little f, and it's, if we're in 2 dimensions, it's f partial x, f partial y. If we're in 3 dimensions, we have an f partial z as well. So it's just where we do each of the partial derivatives for this scalar function little f, and we get a vector. So this gradient of f, this is a vector field. And so the way we can calculate the line integral over this curve C is we take our potential function and we plug in the endpoint of our curve. So this is the potential function at the endpoint. We take our potential function, plug in the start point, and we subtract. So this is a pretty remarkable result that says if we're doing the line integral of a conservative vector field, if we can figure out what the potential function is for that vector field, then in order to do the line integral, we just have to know what the value of that potential function is at the endpoints. So pretty nice. And this should feel kind of similar to a result that we saw all the way back in Calc 1 when we first introduced integration in general. So let's recall the fundamental theorem of calculus. We use this all the time when we're doing integration. And what it said is that if we were doing a regular old definite integral of a derivative, well, the way we actually calculate this is we find the antiderivative and we plug in the endpoint. So we plug in the top limit of integration here, and then we subtract and we plug in the start point, so a. So what we're seeing here with this fundamental theorem for line integration is a very similar idea. If we're doing the line integral of a gradient, well, in some way, the line integral and the gradient operator kind of cancel off. And what we're left with then is just the potential function at the endpoint minus the potential function at the start point. That was the same idea with this definite integral. The integration and the derivative kind of cancel each other off, and then we just plug in the endpoints. So we want to think of potential function little f as an antiderivative. An antiderivative, so little f is really like the antiderivative for this gradient operator. And so the gradient and the line integral really kind of cancel off, and then we're left with just what's going on at the endpoints. So this is going to make calculating certain line integrals pretty nice because we can just plug in the points. Now, one little thing is this theorem is stated if curve C is a smooth curve. It can also be piecewise smooth, and this works works just as well. So that generalizes it. So if the pieces are smooth, then this fundamental theorem still works. All right, so let's try an example. Let's look at the first one here. So we're going to calculate the line integral of a vector field. Our curve C in this case can be any piecewise smooth curve going from the point 3, 4, 12 to the point 2, 2, 0. So just really quick to point out, 3, 4, 12 here is the start point. And point 2, 2, 0 here is the kind of the terminal point, the end point. All right, so that's our curve C. And actually, we don't even need to know what curve the curve actually looks like in order to do this line integral. We only need to know the endpoints. And the reason is because our vector field here is the gravitational vector field that we've looked at, and we've seen that this is conservative. So this gravitational vector field here, the formula is negative little m, capital G. G is the gravitational constant. And what this vector field does is it tells us the mass of a smaller object, or it tells us the force of gravity between a smaller object and a larger object. This larger object is going to be centered at the origin, and our smaller object is going to have this position vector. So vector x here is, well, just x, y, z. It's just a regular position vector, and this is telling us the position of kind of the smaller object that we're dealing with. The bigger object centered at the origin. All right, so this is our gravitational vector field, and we've seen in previous sections that this is conservative. So we know that this is a conservative vector field, and we've actually gone further and figured out the potential function. So our potential function in this case is little f of x, y, z, or if we write that out in vector notation, that would just be little f with vector x plugged in. And this potential function is little m, capital G, divided by the length of vector x. So that's what this potential function is. So if we were to do the gradient of this vector, or of this scalar function, we would get our vector field. So just a quick little note. The gradient of this scalar function is equal to this gravitational field. And that's what it means to be conservative, and that's what it means to be a potential function. All right, so to actually calculate this line integral then isn't going to take too much calculation. We're just going to have to evaluate the potential function. So the line integral of our vector field over curve C is equal to the line integral over this gradient. And in order to calculate this line integral, since we know the potential function, we can just plug in the endpoint, which was 2, 2, 0, minus, and then plug in the start point. So our start point here was 3, 4, 12. So we're just going to plug that in. Okay, well, let's evaluate. So plug each of these in. When we plug the point 2, 2, 0 in, we get little m, capital G, and then the length of that is 2 squared plus 2 squared plus 0 squared. So the length of the vector here that we're plugging in is 2 squared plus 2 squared plus 0 squared. And then same thing for the other point. So we plug 3, 4, 12 in. Again, we get little m times capital G over the square root of 3 squared plus 4 squared plus 12 squared. And perfectly good. Just leave it like that. So these are just constants. All right. So if we know that our vector field is conservative and we have the potential function, calculating this line integral isn't too bad. Let's try one more. So let's look at the next example. So here we have a vector field, and we're going to first figure out the potential function for this vector field. And actually, we've done this in a previous example. So when we found in our notes, when we did this section on finding potential functions, this is a vector field that we looked at. But let's just remember maybe we'll start the process just as a little recall here. So this gradient. So our vector field here is just two components. So our gradient also is just going to be two components. So it's going to be little f partial x, little f partial y here. And the way we kind of work on this, how do we find the potential function, is, well, we look at the first component of our vector field, and that must be equal to the x partial derivative for whatever this function little f is. So the way we started this is we set f partial x equal to that first component, which is 3 plus 2xy. And then from there, we integrate for x. So if we integrate with respect to x, integral of that first term is going to be 3x. Integrate the second term, we get x squared times y. And normally when we find an antiderivative, there's a plus c at the end. But because this is, we're assuming that we're going to have a two-variable function here, it's not just constants that could have gotten canceled off by an x derivative, but it could have been y terms. So rather than plus c, we're going to have plus some unknown function of y. And then once we have this set up for our function little f, then we do the partial. So we differentiate for y. And when we do that, if we differentiate that first term, there's no y there, so that's just 0. If we differentiate the second term, we're going to get x squared. And then we don't know what this is, so we'll just call that g prime when we differentiate with respect to y. And the idea is, now we have an idea of what f partial y should look like, and we set the second component of our vector field, and we're going to compare this. So if we set the second component, f partial y should be equal to x squared minus 3y squared. And if we compare this result and this result, what we see is that the x squareds match perfectly, so that's good. And then the negative 3y squared, well, that must be what g prime is. So we get x squared minus 3y squared is equal to x squared plus g prime y. And that tells us then that g prime must be equal to this negative 3y squared. And if we integrate that, we get that gy must be equal to negative y cubed. And we've gone through the x derivative and the y derivative, so the only thing that could have gotten canceled off that we don't know about with a y derivative is just a constant term. So then we just update our function. And what we ended up with is that our potential function here is, what was it? Well, it was 3x plus x squared y. And then if we filled in what g of y is, or was, minus y cubed plus some constant c. All right, so this was our potential function. And we did this in a previous example, and we did it again just for the practice. Here's our potential function. So now we can use this to help us evaluate this line integral of this vector field where our curve C is given by this parameterization. So our curve C here, the first component is the function e raised to the power t times sine of t. And then the second component of this vector equation is e raised to the power t times cosine. And t is going from 0 to pi. All right, so this is a smooth curve. So we can use our fundamental theorem for line integrals. So if we're interested in calculating the line integral of this vector field, well, we showed that that vector field is equal to a gradient vector field. And we actually figured out the potential function here. So what we're going to do is we're going to take that potential function and we're going to plug in the endpoint of our curve, and we'll plug in the start point of our curve. So t is going from 0 to pi. So when t is 0, if we plug that into our vector formula here, that tells us the start point. And t is going up to pi. So if we plug pi into this, that tells us the endpoint. So we're just going to, plug those in. So when we plug pi in, we're going to get, what do we get when we plug pi into this? Well, sine of pi is 0, so the x value is 0. And when we plug pi into the second component here, we're going to get e raised to the power pi, and then cosine of pi is -1. So we get negative e raised to the power pi. And that's our y component. Now, what do we get when we plug 0 into this vector equation for our curve? So when we plug t equals 0 in, sine of 0 is 0, and cosine of 0 is 1. So in this case, we end up with the point 0, 1. And so when we evaluate, we're just taking our potential function and we're plugging into this. So when we take this first value, x is 0, so that's going to cancel off that and that. And then the only thing we're going to get is this negative y cubed, and then we'll have our constant c there at the end. So when we find this, this will be negative e pi cubed plus c. So that's what we get when we plug in this first point into our potential function. And then we subtract, and then we plug in the second point here. X is 0, so those are all gone. And we end up with just a -1 cubed plus c. And if we simplify this down, well, the c's are going to end up canceling, just like with regular definite integrals. The negative, this double negative here ends up becoming positive, and then this double negative, or actually a quadruple negative, ends up becoming positive as well. So if we were to simplify this down, we would end up with e raised to the 3 pi plus 1. And again, when we have multiple exponents, you just multiply the exponents. And that's it. We found our line integral here. So much easier if we know that our vector field is conservative and we have that potential function that matches up. So here, we didn't really have to use much of the curve here, other than just figuring out the endpoints and the start point. All right, so we'll look more at this in class on Wednesday. So we'll probably do another example and kind of see some implications again on conservative vector fields and this fundamental theorem for line integrals. All right, so we'll see you then. Bye-bye.